All right, A2. Right, so this right here is talking about quantum numbers and the orbitals, right? So you have, three different quantum numbers, right, that we've talked about at this point. We haven't talked about the spin quantum number yet. That becomes much more important down the line. But right for right now, right, there's just simply three of them that we're worried about. The first one, right, is the principal quantum number. Principal, right? That's going to be n, and so that can be, any positive integer. The next, right, is the angular momentum, right? And that's going to determine the shape. Excuse me, right? So that's L. So this is just simply, right, from n minus 1 all the way down to 0. And then the last one is, right, the magnetic, and this is the direction of them, right? And so this is referred to as m sub L, right? And this is just simply from negative L to 0 to L in that case, right? So those are the range of values that you can have. So provide the possible values of L and m sub L for the three quantum numbers for electrons and n equals 3, right? So when n is equal to 3, what you can have are three different L values, right? So you can have L is equal to 2, L is equal to 1, and L is equal to 0, right? So you can have all three of those right there. And then so for all the m sub L values, right, for when you have L is equal to 2, what you can have is m sub L is equal to 0 plus or minus 1 plus or minus 2. In the case of L, what you can have is 0 plus or minus 1, and then L is going to, m sub L for L is equal to 0, right, is simply going to be 0 in those cases. So those are all possible numbers that you can have. How many sets of quantum numbers are possible when n is equal to 5, right? So when n is equal to 5, what you can have is L is equal to 4, L is equal to 3, L is equal to 2, L is equal to 1, and L is equal to 0, right? So you can have 5 different L combinations, right? So that this is the example, right, where you're going to looking at g orbitals, right? That's what the L equals 4 is for. So then for each one of those, right, the equation that you could really use in that case is that the number of orbitals that you have, or the number of possible, m sub L values that you can have, right, is always going to be equal to L plus 2L plus 1, right? Is always going to be equal to that value in those cases, right? And so in this case right here, right, there's only one that you can have for here, right? So 2L plus 1 for L is equal to 1. So that's 2 times 1 plus 1 gives us 3. So this is 3. L is equal to 2, right, gives us 5, 7, 9, right? It always goes up by 2, right? Because you're always adding one more plus or minus to the system, right? So you have 9 plus 7 plus 5 plus 3 plus 1, right? That comes out to being 25. What does it mean if two orbitals are degenerate, right? And I talked about this, in the previous problem, but when two orbitals are degenerate, right, they have the exact same energy. They're technically two different, quantum systems, right? Because they're going to have different quantum numbers, right? When you have a px and a py, right, they have different quantum numbers, right? They have two different ml values, or m sub L values, sorry. But when they're atomic orbitals, they're going to have the exact same energy, right? And so they're going to be degenerate. And so that's, what the definition is, right? That they have the exact same energy. In the case of, when L is equal to 3, how many orbitals are, how many degenerate orbitals are possible? Right? You have the possibility of having, in this case right here, right, 7 orbitals, right? Because that's going to be the f orbitals, right? When L is equal to 3, right, you're looking at the f orbitals, and so there's 7 orbitals, right, that can be degenerate in that case, right? You have your z cubed and all the other things like that, right? In those cases, right, all 7 of those are going to be at the exact same energy, most of the time, and so that's how you get that value, right? Is just simply knowing, right, that you have 7 L equals 3 orbitals in that case, right? And just because they have different m sub L values, short of, going into bonds and having any kind of interactions, with a magnetic field, they should stay exactly the same, energy wise, right? They should stay degenerate. Cool.